So yeah, my name is Timo Drick and I'm from Germany, as you already heard. I'm Android developer since 12 years now. And today I will show you how you can create pixel shaders to make your apps outstanding. First, I will give you a short introduction. What are pixel shaders and show you some samples. Then I will show how you can use it in Compose. And then we will start with drawing simple shapes using shaders, and then go to animations. And at the end, I will also talk a little bit about compatibility. Maybe if there's some time left, we can do a short live coding session, but we will see. And then I will show a summary. So let's start. Here you can see some pixel shaders used as background. So on the left, in these triangles in the background are drawn using a shader. And also in the middle, you can see this background is also drawn with a shader. This app for me. And on the right, you see the Compose jet lagged app. This is a sample app from the official sample app from Compose. And there you see also a pixel shader at the top, which is animated. So you can also use shaders to animate buttons, for example. Here I do have a shine animation for the button. Or you can use it to show loading animations in your app. Here's another loading animation. Yeah, so you can also go crazy with this shader stuff. For example, if you want really a user to push a button, then you can implement a burning button here. Or maybe then the user do not want to click on it. I don't know. You will have to decide. Or here you can do a 3D animation for loading. It's also programmed just with a shader. Or you can also implement shaders to do transitions in Compose. Here you see a certain transition. By the way, all the shaders I show you today, I have an open source project where you can see the code and also compile it and use it as inspiration. So yeah, maybe you know this already, but shaders are used anywhere in computer graphics today. So also Android using shaders to draw, compose, and also the old legacy UI system is drawn by shaders. But until Android 13, you do not have really a way to use custom shaders inside of your normal graphics or from your user interface. But in Android 13, AGSL was introduced, Android Graphics Shader Language. But it's a complete new language, but it's based on very old pixel shader definitions from OpenGL, so GLSL. So the language is very similar to this. So yeah, as I already told you, shaders are used anywhere, so also in games. And when your device supports OpenGL or Metal, Metal is this thing from Apple, it's used on macOS and iOS. And OpenGL you can use also in the browser with WebGL. So everywhere you can use shaders. So the things I will show you today, it's not only applicable to Android, you can also use it for other things. Yeah, let's see what are shaders exactly. So you maybe already know canvas draw operations like draw a circle, draw a rectangle, or draw a triangle, or some more complex shapes. And then you can use shaders to fill these shapes. There are built-in shaders, like just a solid color or a linear gradient, or here as an example, radial gradient or an image. In addition, with Android 13, we now can implement custom shaders. So how this works, at the end, it's you have a small program which runs directly on the GPU, on the graphics processor unit, also on your Android device, and you get as input, you get a coordinate from the pixel, and you have to return a color. So for every pixel on the screen, you get your function, your main function gets called once with a pixel coordinate, and then you have to return the color. So here you see a simple program which just has this main function. So this is the entry point, and as parameter you get a float2 frac coordinate, and you have to return a float4. Float2, I will explain a little bit more in detail later, but at the end it's just two floating point values in an array you can think of, or you can think of it as a vector with two components, and this float4 is a vector of four components, or an array of four values, floating point values. And in this case, I just return float4 with the values 1, 0, 0, 1. So red is 1, and green and blue are 0, and the alpha value is 1. And then on the screen, you will see just a rectangle, a red rectangle. Yeah, also important to note that the value range for colors are between 1 and 0. So 1 means it's completely red, and 0, it's no red component. Or in this case, there's no green and blue, but fully saturated red. The alpha channel you can use to have some transparency. For now, we just set it to 1. So 1, it's opaque, so you don't see the background. Yeah, just have a red screen is a little bit boring. So to make it a little bit more interesting, we can use the input variable fraccord, the x component of the coordinate, and divide this by 200. And yeah, for this now I just made sure that the size of my window is exactly 200 by 200. So in this case, the pixels on the left do have a fraccord.x value of 0, and on the right it would be 200, and when I divide it by 200, I get exactly 1. So here you can see how I can implement a gradient with a custom pixel shader. Some more basics. This float2, you can also write vec2. As I said, you can see it as a vector. That's later handy when we want to do some math with our values. So we can use vector math. Inside of shaders, there are some support for doing multiplying or dot products or something like that. Also, you can access different paths, as you already saw. For this float2 with the coordinates, I can access the first coordinate with dot x, and the second with dot y and dot z. Also, when I interpret this value as color, I could use RGB, but it's not a type. It's just how do you interpret the values. So you can use both notifications, both notations, anyways. So it's up to the programmer. So now let's see how we can integrate this in Compose. The shader code itself. Here's a sample shader code to draw a checkerboard pattern on the screen. I will not go to in detail now, but you can see that's just a variable, and I can write this in Kotlin code and just write the shader code inside of a string variable. I can use this annotation, add language, AGSL, and then I get some syntax highlighting in Android Studio. And then to use it inside of my compose components, my composables, I can define a custom modifier. And here I use this draw with cache modifier. This is used to draw some canvas graphics and also cache this, so we do not have to create new instances of our variables every time. And in the onDrawBehind method, we then draw our canvas. In this case, it's just draw a rect over the complete screen or the size of our modifier. And here you see the new class runtime shader. This was introduced in Android 13. And there you can just put your shader code in. You have to provide it as a string variable, and then create a shader brush out of it, and then you can use it on all draw operations. Yeah, as I already shown, draw rect and also draw circle and stuff like that. Here's an example for composable. So when you want to have a complete screen filled with your shader, and you just create a box with a fill max size modifier and add your background shader. This would then look like this. Let's assume we want to have exactly 10 by 10 checkerboard patterns on the screen. In this case, I have to provide my shader a scaling because when I write the shader, I do not know the exact size of the screen. And for this, there's I can use uniform values. In this case, uniform float 2 with iScaling. This iScaling is just a name. I can use any name I want. And float 2 with 2 components. And then the rest of the code is identical to before. And I just multiply my record with this iScaling to get the right size. Inside of my shader code and inside of my compose code, I now have to set this float uniform. So I have to provide the name, iScaling, and then the values. And here for now, I provide 10 divided by this width and height. So I get exactly 10 by 10 checkerboard patterns. But as you can see, it's a little bit stretched. So maybe I only want 10 checkerboard patterns in the horizontal axis. So then I will divide by the width for both variables, also for the y. And in this case, I have exactly 10 checkerboard patterns in the horizontal axis, but it's in the vertical axis, it's more, or depends on the height of the device. But the aspect ratio is now 1 by 1, so it's exactly square patterns. Other thing, when I want to have a specific physical size of my checkerboard pattern, I have to convert dp, which are the density independent pixel measurement of Android. I have to convert this into pixel, and then I can use this for scaling. And this then will lead to almost equal physical sizes of the checkerboard pattern, even when you show it on different devices with different pixel densities. So that was the part of compose. Now let's discuss how we can draw something. Maybe a little bit more difficult, and it's not straightforward as canvas drawing operations. So when I want to draw a shape, I need to have a distance function for that shape. So this means when I have a pixel coordinate, then I need a function which tells me the distance from this coordinate to the outline of the shape, or the minimal distance. So here's a function for a circle. In case of a circle, it's very easy because I can just calculate the length of the vector from my actual from my current coordinate to the center of the circle. So there's also a built-in function in shaders, which is called length, and there you just subtract from your coordinate the position where you want the center of the circle, and then from this you subtract the radius, so that you get exactly 0 at the outline of your shape. Here's the shader code. So in this case also, I assume that we have a window of 200 by 200. Then when we want to center our circle, then the circle position would be 100, 100, and the radius also 100. And then we can calculate the distance by taking this length function and subtracting the radius. And then we can decide if we are inside of our shape or outside, depending on if the distance is smaller than 0. In this case, we would be inside. And we use this value then to calculate the color. I inverted the color because I want to have black inside and white outside. And in this case, I use the float 3. So this means for all color components, I use the same value. So it's 0 when it's inside, it's for every component, and 1 when it's outside. And so here you see the circle. One thing maybe you notice, it's that the edges of the circle are very pixelated or sharp, and you have this rectangles at the edges. And normally you don't want this, so there's a function to get rid of this pixelation, and it's called smooth step. It's also built in shaders, so you can just use it. You give it a starting point and an end point or a range and your function value, and then it will return a value between 0 and 1, and it will do a smooth transition between them. So let's apply this to our shader. So in this case, we have this inside function. We use a smooth step from 0.0 to, in this case, B, and it's 20 for the sample. And then we just give the length. And then it will look like this. So we have now 20 pixels of smooth edge here. We can also change this value. For example, when we use 80, then it looks like this. Or we can make it smaller. Then we get a more sharp edge here. This is a value of 10. And here's the value of 2, I think. But then you can see pixelation again a little bit. There are many other distance functions you can use. On the website from Ingo Kiles, you have for every simple shape you can imagine, you have distance functions. Here are some samples of a square or a triangle, hexagon, and also some circles and parts of circles. Maybe simple shapes are not enough, so then we want to combine shapes to create more complicated ones. This is also very easy. For example, when we want to subtract two circles from each other to get a moon, as you can see on the left, then we can use the max function. So we use the maximum from two distance functions. And for the second distance function, we invert. So we use the minus sign for this function which gets subtracted. And when you want to have a union, we just use a minimum of two signed distance functions. And for intersection, we just use the maximum without inversion of one component. Other things we maybe want to do is some deformations of our shapes. In this case, we do not change the distance function, we just change our coordinate system and deform it. I will show you first how to do a rotation. So here's a rotation function. This will return a matrix, a 2x2 matrix. And as I said before, we can do some simple vector math here to rotate our coordinate system. So we use our frac chord and multiply it by this rotation matrix, and then we get back also a coordinate. Maybe you remember this from school math, but it's not so important. You can just use it as a building block for your shaders. But it's important that this will rotate around the coordinate 0, 0. So you have to move your coordinate system before using this rotation. Sorry. So now let's see a sample. On the left, you see this rotation function and also this SD box function, which is a rectangle. And as you can see on the right, the code, we first move our frac chord to the center by subtracting the center position. And then we want to rotate it by 45 degrees. We have to convert this degree into radians because these functions inside of the shader needs radians as input. And then we can call our rotate function with radians. And here, as you can see, I multiply this rotate function with my frac coordinate. And after this, I calculate the distance to my rectangle. This is SD box function. In this case, the rectangle is 100 pixel width, and the height is 30. The width is 100 pixels, and the height is 30 pixels, I think. And then it will look like this. So it's rotated 45 degrees. We can also shrink or stretch our coordinate system. So in this example, I just multiplied the x-axis by 2, which will shrink the y-axis by 2. And just using this methods I showed you before, you can get already amazing effects. Here, I just used triangles and rotated them a little bit and used different colors for the triangles. And then you can get a background like this. Here's the shader code for this. As you can see, it's just many triangles with different rotation, and also I use this smooth step function with different values for the range. Okay, now let's start with the next part, how we can support animations. For this, we also use a uniform to forward some values to our shader. And here's the compose code I need to change. First, I define, let's assume we want to do an infinite animation loop. So I use this compose function, remember infinite transition, and then use this infinite transition and animate a float out of it. Important here, the initial value I selected to be 0 and the target value 1. That's important because inside of my shader code, it's much easier to do the math when I have a value between 0 and 1. And then I can specify the length of the animation. So how long one loop will be. And in this case, I decided to have 2 seconds. And also important to note that you have to set the easing function to linear easing. Otherwise, we could get some deformations in time. And here at the bottom, you see I just forward this value with this set float uniform function you already know with itime, and I use this animation value. Compose then will automatically update this value on every frame. So inside of our shader code, it's now very easy. We just change the angle from the static 45° to this itime, and I also multiplied it by pi times 2, because in radians, pi times 2 is exactly 360°. So we get a value between 0 and 360°, and then it will start again from 0. I have this minus in front to have a clockwise rotation. Otherwise, it would be counterclockwise. Yeah, let's see a little bit more complex sample here. As I showed you already at the beginning, the sample, and here's the code to draw this animation. You can use it as a loading animation, for example. At the end, it's just a for loop which drawing, which are using this SD box function, which drawing rectangles. But in this case, I do not rotate the box itself. I will just change the size of the box and also the smooth step function a little bit. Yeah, maybe another interesting animation is this shiny button. Here's the code for this shiny button. I do not have to use any complex rotation things or something like that. It's just simple addition, multiplication, and some smooth step functions to reach this. So it's very little code you need to support this. Okay, so now let's discuss a little bit about compatibility. As I said already, AGSL was introduced in Android 13, but it's based on GLSL. AGSL itself is not really invented by Android. It's more or less SKSL, which is Skia shading language. So Android uses Skia to draw everything. It is used in Compose and also in the Android legacy view system. And Skia do have this custom shader support, and Android just renamed it. But SKSL itself is also based on GLSL, which is from the OpenGL shading. It's a OpenGL shading language, and as I already said, it's supported on almost every device. So it's possible to port your AGSL shader to GLSL, and then you can use it on every device. Also, when you want to do some graphics inside of a browser, you can use WebGL, and there's also shaders support. and on iOS and Mac, you can use Metal. Yeah, and on these shaders are different languages, but they are very similar. So you don't have to change much of your code. Yeah, for OpenGL, the coordinate system is a little bit different, but other than that, you can almost use the same code. Okay, yeah, I think we have some time left. So I prepared a small live coding. So how you can develop a shader. In Android, when you program code in Kotlin, then you have to compile it and put it on the device. Of course, for now in Android Studio, we have this live preview. That's fine, but what about shaders? This live preview does not work with shaders, but fortunately, this custom shader support is also implemented in Compose for desktop, and I wrote some code to be able to change to use shaders on my disk and then draw it directly on a Compose for desktop app, and I can monitor the file changes, and then we will see we can instantly see changes in our file. So that's just here. This is Android Studio, and here we see very simple shader code. Let me start the application. So I will put this in front. So, and when I change here, this is my code for changing the pixel color, calculating the pixel color. So for example, let us show some green value that everything is working. Now, when I save this file, my code will detect this change and will compile the shader again and show it here on this application. It's a Compose for desktop application. So yeah, here you see it's just green. Now, if we want to have this gradient I showed you before, then I can use this vec coordinate, the x value. When I use it this way, then nothing changed because I have to divide it by a number. For example, I can divide it by 200 or 400. And now I don't know how big my screen is, but I also have a uniform here, I resolution, and in this variable, I do have the resolution of the screen. Not the resolution of the screen, the size of my window. So I can use this, and then I get exactly a gradient from 0 to 1 on the right. Yeah, I have also this iTime uniform. So when I use this and use it now for, this is the blue component, then you see it will, yeah, it will go to blue from green. Yeah, it's a little bit annoying, so I will set it back to 0. So now let's see, we have this circle distance function. And now we just use the distance here. Oh, I forgot. Yeah, you have to use a semicolon here again. It's not Kotlin, it's a different language, so it's similar to C. And now, yeah, you can see here we have the circle, but it's not in the center. So let's move our coordinate system to the center. For this, we calculate first the center. I can use this I resolution and divide it by 2. This is the center. And then here, I subtract the center. And now the circle is in the center. And yeah, I can change here the size of my window, and it will be in the center every time. Yeah. Yeah, now to the next point. We want to have the smooth step again. So then change this, the distance, and use the smooth step from 0 to, yeah, we can define here the gradient range and the old distance. And now you see that it gets a little bit fuzzy. I can increase this value 100, 200 as I want. Yeah, that's it to the live coding. Also, I can show you this sample app I created. I also have a GitHub project where the source code is. You can look up everything I showed you today. Just let me show the device. So here you see the sample app. And for example, here's the loading wheel. Yeah, I also did some playing around here. You can also draw a chart in 3D, but then you come to the limits of the AGSL language. Here's a certain animation. So yeah, you can see it will then reveals another composable at the back. Okay, so that's to the live coding part. Okay, now we come to an end. In summary, so as you can see, it's possible to create amazing effects using AGSL, but it's also a little bit more complicated. The learning curve is very steep, but you don't need a master degree to to calculate simple shapes and stuff like that. But if you want to just draw circles or rectangles and stuff like that, maybe it's easier to use the canvas drawing API. But yeah, when you spend some time and try to learn AGSL, then you can really get an app that stands out to other apps. Yeah, thank you for your attention. Here are some references. As I said, here first is the GitHub project with the sample app. It also shows the Compose for Desktop code to do live code shader coding. And I do have some Medium articles where I go more in detail how to draw these shapes and stuff like this. And yeah, distance function from Ingo Igles. And also there are some websites, shaders.skia.org. You can also use them to do some live coding. So you're on this website, you can enter your shader code and then you'll see instantly the result. And there's also this great community, shadertoy.com. And there you have a community which develops shaders, and it's very inspiring. So maybe you want to have a look there. So yeah, you can, on this website, you have many shaders and you can click on everything and see the source code. For example, for this shader, you see here, it's just 162 lines of code. And yeah, it's very great community. Here you can browse and it's so many, there are so many shaders and every day there come new ones and also very crazy ones in 3D. But keep in mind for this AGSL shaders inside of Compose and Skia, there are some limitations. You cannot go crazy with 3D. Then yeah, you have to check, or maybe then you have to do an OpenGL shader. Okay, so that's all from my side.
Wow, thank you very much, Timo.
You're welcome.
Yeah, folks, I'll give you a few minutes, a couple minutes here to write your questions in the comments, and then Timo can review them. In the meantime, I guess we'll just chat. Yeah, wow, that was a nice education on an area. I feel like not a lot of engineers get to like really touch.
Yes, yes.
And,
yeah, that's right. Yeah.
And a lot of them, and a lot of people who don't touch it, then continue to be afraid of it.
Yes. Yeah, to be honest, in my daily work, I'm Android developer, and also I never use it really. Yeah, for me, it's just a hobby project. But yeah, when you know a little bit, then with very simple math, you can get amazing effects.
Interesting. I get the feeling something like this is, you need a good understanding of graphing to really communicate, like to like produce something from concept to actual reality. I find that that tends to be the ambiguous problem is how exactly do you do graphing? And that's not.
Yeah, I think also one important thing, maybe normally the workflow would be that you have a designer and the designer will create some graphics and then you have to import it to Android. But in this case, this will not work because, yeah, when you try to replicate the design with a shader, then maybe it's not possible or it's very complicated math. So it works more when you do it as a developer yourself, and or maybe you have to work together with the designer.
Yeah. I mean, I guess if you, yeah, I it's such a wild area. I don't know. I've definitely been afraid of it before. I think I've almost touched it before, and I was like, design. I think we should rethink this. Little wimpy.
Yeah. Yeah, of course, but yeah, not many developers doing it. So when you integrate it into your app, then it's outstanding, and yeah, you can, when you want to spend time there, then I think it pays back, maybe.
That's the thing. I mean, there are times where you need it, and therefore it's kind of there's no way around it. But it's I feel like a pain point or a reason why it's reasonable to be afraid of it is maintenance. Like if you had to really put a lot of work into figuring out how to do it, then how is somebody going to show up, figure out what you did, and then modify it?
Yes, that's correct. Yeah, but for example, when you have now with Material 3 design, you have this variable colors or something like that. Yeah, then you cannot just use an image as background, for example, because you want to change the colors depending on the current UI or what the user selected. And this is a great use case for shaders because there you can use these uniforms to forward the colors to the shader, and then it will automatically change the pixels. But yeah, of course, it's it's difficult to maintain, or at least you have to to make sure that your team is able to change the code and understand it.
Yeah, the tricky part. Yeah.
Yeah.
I'm not seeing it. Seems Well, it doesn't matter because I mean sometimes people just the question askers are the ones who watch it, the actual recording, as opposed to showing up to the live session. So here's the way it goes sometimes.
Yeah.
Yeah, but thank you so much for presenting, Timo.
You're welcome. Thank you.